In chemistry, colligative properties are properties of solutions that depend upon the ratio of the number of solute particles to the number of solvent molecules in a solution, and not on the type of chemical species present. The number ratio can be related to the various units for concentration of solutions. The independence of the nature of solute particles is exact for ideal solutions, and approximate for dilute real solutions. Here we consider only those properties which result because of the dissolution of non-volatile solute in a volatile liquid solvent. They are independent of the nature of the solute because they are due essentially to the dilution of the solvent by the solute. The word colligative is derived from the Latin colligatus, meaning bound together. Colligative properties include relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, osmotic pressure. For a given solute-solvent mass ratio, all colligative properties are inversely proportional to solute molar mass. Measurement of colligative properties for a dilute solution of a non-ionized solute such as urea or glucose in water or another solvent can lead to determinations of relative molar masses, both for small molecules and for polymers, which cannot be studied by other means. Alternatively, measurements for ionized solutes can lead to an estimation of the percentage of ionization taking place. Colligative properties are mostly studied for dilute solutions, whose behavior may often be approximated as that of an ideal solution. Relative lowering of vapor pressure. The vapor pressure of a liquid is the pressure of a vapor in equilibrium with the liquid phase. The vapor pressure of a solvent is lowered by addition of a non-volatile solute to form a solution. For an ideal solution, the equilibrium vapor pressure is given by Raoult's laws, whereas the vapor pressure of the pure component N is the mole fraction of the component in the solution for a solution with a solvent and one non-volatile solute, and the vapor pressure lowering relative to pure solvent is, which is proportional to the mole fraction of solute. If the solute dissociates in solution, then the vapor pressure lowering is increased by the Van 't Hoff factor, which represents the true number of solute particles for each formula unit. For example, the strong electrolyte MgCl2 dissociates into 1 Mg2 plus ion and 2 Cl minus ions, so that if ionization is complete, I equals 3 N. The measured colligative properties show that I is somewhat less than 3 due to ion association. Boiling point and freezing point. Addition of solute to form a solution stabilizes the solvent in the liquid phase, and lowers the solvent chemical potential so that solvent molecules have less tendency to move to the gas or solid phases. As a result, liquid solutions slightly above the solvent boiling point at a given pressure become stable, which means that the boiling point increases. Similarly, liquid solutions slightly below the solvent freezing point become stable, meaning that the freezing point decreases. Both the boiling point elevation and the freezing point depression are proportional to the lowering of vapor pressure in a dilute solution. These properties are colligative in systems where the solute is essentially confined to the liquid phase. Boiling point elevation is colligative for non-volatile solutes where the solute presence in the gas phase is negligible. Freezing point depression is colligative for most solutes since very few solutes dissolve appreciably in solid solvents. Boiling point elevation. The boiling point of a liquid is the temperature, and M is the molality of the solution. The boiling point is the temperature at which there is equilibrium between liquid and gas phases. At the boiling point, the number of gas molecules condensing to liquid equals the number of liquid molecules evaporating to gas. Adding a solute dilutes the concentration of the liquid molecules and reduces the rate of evaporation. To compensate for this and reattain equilibrium, the boiling point occurs at a higher temperature. If the solution is assumed to be an ideal solution, Kb can be evaluated from the thermodynamic condition for liquid-vapor equilibrium. At the boiling point, the chemical potential μA of the solvent in the solution phase equals the chemical potential in the pure vapor phase above the solution, where the asterisks indicate pure phases. This leads to the result, where R is the molar gas constant, M is the solvent molar mass, and delta HVAP is the solvent molar enthalpy of vaporization. Freezing point depression. The freezing point was introduced in 1891 by Wilhelm Ostwald. Ostwald classified solute properties in three categories: colligative properties, which depend only on solute concentration and temperature, and are independent of the nature of the solute particles; additive properties, such as mass, which are the sums of properties of the constituent particles and therefore depend also on the composition of the solute; and constitutional properties, which depend further on the molecular structure of the solute.